Most powerful computers you've never heard of. An ancient Greek relic was found in a shipwreck off the coast of Antikythera in 1901. It had 37 interconnecting bronze gears according to 3D X-ray scans, allowing it to model the motions of the sun and moon and anticipate eclipses decades in advance. Hey everyone, how you doing today? Before we proceed with this video, don't forget to subscribe to our YouTube channel. Kindly click on the notification bell to get updates on our exciting content. Today, join us as we go down the memory lane of some of the most powerful computers you've never heard of. Let's dig in. The Antikythera mechanism, built around 100 or 200 BC, shows a sophisticated early computer that would not be witnessed again for at least 1,000 years. Of course, this computer didn't function the same way that current digital computers do. It works based on analogies. The gears were designed so that the motion of specific dials are comparable to the motions of the sun and moon. It's a computer that works in analog mode. The quantities of interest in analog computers are physically represented by something physical, such as the number of times a wheel is turned. In contrast, digital computers deal with symbols such as zeros and ones. In fact, until the 1960s, the world's most powerful computers were analog. With the introduction of solid-state transistors, digital computers exploded onto the scene. Almost everything is now digital. Analog computers are unfamiliar to the majority of people, but that could all be changing now. Because transistors are approximately the same size as atoms, Moore's law, the theory that you can duplicate the number of transistors on a chip every 2 years, is hitting its limit. Simultaneously, advances in machine learning are putting digital computers to the test. A new generation of analog computers could be the answer to these problems. Predicting the tides has been one of humanity's most difficult issues for millennia. As a result of a miscalculation of the rising tide, Napoleon and his soldiers came dangerously close to drowning while crossing the Red Sea, and sailors needed to be aware of the tides in order to navigate their ships into port without running aground. The majority of coastal places on the planet experience 2 high and 2 low tides per day, but their exact time and amplitude vary. Local factors such as the depth of the seabed and the contour of the shoreline contribute to this. Pierre-Simon Laplace developed a series of sophisticated differential equations to describe the tidal flow of the oceans in the late 1700s. They didn't have an analytical answer at the time. Therefore, they were essentially useless. However, Laplace discovered something important in formulating his equations. Tides are governed by only a few astronomical commonesses, including the sun, the moon, and the eccentricity of the lunar orbit. Each of these components contributes a sine wave of a specific amplitude and phase to the total tide curve. The tides may finally be forecast if someone could figure out how to mix these frequency components correctly. After over a century, William Thomson, later Lord Kelvin, took up the subject in the 1860s. After completing many expeditions to lay the first transatlantic telegraph line, he developed a fascination with the sea. As a result, he concentrated all his scientific efforts on measuring and forecasting the tides. At the time, tide gauges employed a buoy to record the height of the sea on a roll of paper. Kelvin figured out how sine waves with Laplace's frequencies could be combined to form the observed tidal curve. The trick was to use the work of Joseph Fourier, a French mathematician who demonstrated how to decompose any function into a sum of sine waves. While applying Fourier's analysis to tidal curves was simple, the processing required was tremendous. Most English scientists met the work with skepticism, but Thomson was intrigued by it. At the young age of 17, he wrote his first paper, which was a defense of Fourier. Derek Kelvin's harmonic analyzers were the foundation for the differential analyzer, a seminal analog computer, and his tide prediction machines remained in use long into the 1960s. They were eventually revamped with 26 frequency components and utilized to organize the Allied invasion on D-Day. The Germans anticipated an invasion at high tide to reduce the time Allied troops would be exposed on the beaches. As a result, they erected millions of barriers that would be submerged by mid-tide, many of which were rigged with exploding mines. On the other hand, the Allies recognized the impediments and changed course. They want to start the invasion at low tide instead. As the water level increased, demolition crews could first clear passages through the obstruction. Then, the major forces could come through the holes. This would also allow landing craft to depart without being stranded. Because the low water periods at the 5 landing beaches differed by nearly an hour, the invasion times were staggered based on tidal predictions. During World War II, analog computers were used in a variety of ways. Dive bomber aircraft would drop out of the sky at as much as an 80-degree angle directly at their objectives, and their quick descents made them tough to shoot down. As a result, the United States began looking for technologies that automatically direct guns at dive bombers. The majority of the remedies presented fell into one of two categories. Lord Kelvin's analog machine was one of them. Others were essentially calculators that could be used quickly. The abacus and other mechanical calculating machines had been around for millennia, but they were much too sluggish to reply to dive bombers. Electrical pulses were used in these new calculating devices to speed things up. The committee discussed giving these gadgets names based on the pulses they generated. However, member George Stibitz proposed a broader term, digital, because these computers are based on numbers, or digits. This is where the phrase digital computer comes from. Digital, on the other hand, would have to wait. David Parkinson's ingenious analog machine won out over all the other concepts. Parkinson had been working on an automatic level recorder, a device for charting telephone data, at Bell Labs in New York. An operational amplifier, or op-amp, was a recently invented analog electric device by Bell Lab researchers. It could execute mathematical operations like addition and multiplication using voltages. They used these op-amps to build an analog computer that could solve anti-aircraft gun ballistics equations. The M9 gun director, as the computer was known, could quickly calculate the correct trajectory and few settings using radar and optical sights to obtain the speed, altitude, and direction of hostile planes. To determine which way the rifle was pointing, potentiometers were utilized. Although this was not the first electric analog computer, it was significant. During World War I, it took about 17,000 shots to bring down a single plane. It took only 90 minutes in 1943 after the M9 was invented. During World War II, the United States made significant investments in analog computers. The creation and construction of the Norden bombsight, an immensely complicated mechanical analog computer, was the third greatest single expense in their total military budget. They didn't receive their money's worth, unfortunately. The Norden bombsight was designed by eccentric Dutch inventor Carl Norden to enable high-accuracy aircraft bombing. It used 64 separate simultaneous algorithms, one of which corrected for the Earth's rotation when the bomb detonated. One of the world's most jealously guarded secrets was the Norden. To control the technology and keep it out of the hands of the enemy, American bombardiers carried handguns designed to destroy it in the case of a crash. Despite the excitement and financing, however, the Norden did not perform as expected. The production of almost 2,000 delicate pieces necessitated exceptional precision. The issue with analog computers is that the actual equipment is merely a representation of reality. As a result, every error in the components leads to errors in computation. And because there will always be some slop in the connections between pieces, repeating the calculation will not get the same result. Bomber crews using the bombsight were unable to attack important Japanese war infrastructure during the American assault against Japan. Finally, the U.S. abandoned its precision bombing strategy in favor of blanketing entire Japanese cities in napalm. Digital computers gained popularity as the conflict proceeded. Bletchley Park's digital and electronic Colossus machines were crucial in cracking German codes. The military in the United States invested in ENIAC, a massively complicated and expensive digital machine. Its purpose was to make the calculation of land artillery firing tables faster. At the time, differential analyzers, analog mechanical computers based on Kelvin's harmonic analyzer, were used to calculate these. ENIAC showcased the capabilities of digital computers, despite not being completed until after the war. Many people consider it to be the first modern computer. The discovery made by Claude Shannon in his master's thesis in 1936 was the key to this digital revolution. He demonstrated that the basic building blocks of Boolean algebra might be used to perform any numerical operation: 2 values, true or false, also written as 1 or 0, and 3 operations: and, or, and not. As a result, digital computers are the most adaptable computing devices available. Each analog computer, on the other hand, is an analog for only one sort of issue. Furthermore, because digital computers work with ones and zeros, they are more noise resistant. A huge inaccuracy would be required to confuse a 1 for a 0, or vice versa. In analog computers, however, even minor errors can accumulate and eventually overwhelm the signal. In today's world, everything is digital. Our phones, computers, and internet data centers, as well as television and radio, are now broadcast in digital format. The benefits are clear. That's it on the most powerful computers you've ever heard of. What do you think? Do you believe these computers are worth seeing the light of day? Let us know what your thoughts are in the comments section below. If this video was insightful for you, then go on and like it. Please kindly subscribe to our channel and click on the bell icon for more of our updates.